Okay, so today we're diving into something pretty fascinating, I think, at least for me, Bohr's correspondence principle. And I know, you being a philosopher, this is going to be right up your alley. It's not just about physics, right? This is about how, like, scientific ideas change and evolve over time. What's the link between the old and the new?
Absolutely. It really gets to like the core of what makes a scientific principle really like a bedrock thing.
Right, right. So I guess our goal today is to try to unpack all of that. I mean, what did Bohr really mean? Like, there are all these different interpretations, even from Bohr himself. And then, how important was it to developing quantum mechanics?
And I think it's key for you to realize this is a living debate. We're not just digging through dusty history here. Like how people understood it back then is different from how we see it now. It makes it even more interesting from a philosophical angle, right? Like how do we know what counts as progress in science?
Yeah, that's a good point. So we've got a lot to cover today. We're pulling from like historical accounts, philosophical papers, the whole deal.
It's a really fascinating mix of sources.
Okay, well, let's get to it then. So I guess the first thing we got to talk about is Niels Bohr himself, right? I mean, he was the central figure in quantum theory, but was there anything about his thinking that other scientists back then like had problems with?
Oh, for sure. Bohr, he lived from 1885 to 1962. No doubt, like he was crucial to quantum theory. I mean, his work on the atom, the Bohr model, that won him the Nobel Prize in 1922. But he wasn't just like doing calculations. He was thinking really hard about what this new physics meant for us.
Like philosophically?
Totally, yeah. Like his debates with Einstein, the whole Copenhagen interpretation thing, that's still hugely important today.
Right, right. Okay. So this correspondence principle didn't just come out of nowhere, right?
No, not at all. It came about during what we call the old quantum theory, which lasted from about 1900 to 1925, kind of like a stepping stone. They knew classical physics was breaking down at the atomic level, but they didn't yet have like a full replacement.
Yeah, like they had some successes, but also some big problems.
Exactly. I mean, they explained some things that classical physics just couldn't touch, like, certain atomic behaviors. But it was all kind of piecemeal, like they were patching together classical and quantum ideas. And that lack of a solid foundation, that's ultimately what led to the development of the modern quantum mechanics we know today. Like in the mid-1920s, Heisenberg came up with matrix mechanics, and then Schrödinger had wave mechanics.
Okay, so to see where the correspondence principle fits in, I guess we should talk about the specific things physicists were struggling with back then. And I guess Rutherford's model of the atom is a good place to start, right?
Absolutely. Rutherford's model, with the nucleus in the center and the electrons orbiting around it, that was a huge step. But immediately they hit a problem, a big one. According to classical electrodynamics, if you have a charged particle accelerating, like an electron going around the nucleus, it should be constantly losing energy by radiating electromagnetic waves.
So the atom should basically collapse.
Yeah. The electron should spiral into the nucleus really fast. That's what classical physics said. But obviously, atoms are actually stable. So something was wrong.
So Bohr came in and tried to solve that stability problem with his two postulates in 1913.
Exactly. And these postulates were radical. I mean, they broke with classical physics in a big way. The first one said that, yeah, electrons are orbiting the nucleus, but they can only exist in these special orbits, which he called stationary states. And while they're in these stationary states, they don't radiate energy at all, even though they're accelerating.
So electrons going around in circles but not radiating any energy, that seems pretty weird from a classical point of view.
It is. It's completely against what classical physics would predict. But Bohr needed it to explain the stability of atoms. Then the second postulate, that one dealt with transitions. Bohr said that radiation, like light, is only emitted or absorbed when an electron jumps between these stationary states. So it goes from one energy level to another, let's say from an energy level,
Right.
and the frequency of the emitted or absorbed light that's given by the Bohr-Einstein frequency condition.
Where's Planck's constant, right?
Exactly. Planck's constant, that little h, that's telling us that energy comes in these tiny packets. It's not continuous. And for you, thinking about scientific revolutions, this is a big deal. I mean, this equation wasn't just tweaking classical physics. It was introducing a completely new relationship between energy and frequency. It was quantized.
Right. So instead of a continuous spectrum of light being emitted, like classical physics would predict, you have these specific frequencies corresponding to the jumps between energy levels.
And here's a fun little historical tidbit. Today, we know that this radiation emitted during these transitions is a photon, right? But Bohr himself, He actually didn't fully accept the idea of photons until like the mid-1920s.
Really? Why not?
Well, at the time, the photon concept seemed like it just couldn't be reconciled with stuff like interference and diffraction, things that we see with waves.
Hmm.
Bohr was like, if light is just these little packets of energy, how do you explain waves spreading out and overlapping? He was really attached to the classical wave picture of light because, in classical physics, you can analyze light into its harmonic components.
And that turns out to be important for the correspondence principle.
It's totally crucial. It was only later, when there was really solid experimental evidence for photons, like the Compton effect and things like that, that Bohr finally started to come around. But back when he was developing the correspondence principle, the wave picture was still really central to his thinking.
Okay, so we have these stationary states, and we have these quantum jumps, and we have these specific frequencies of light being emitted. But how did Bohr actually figure out which orbits were allowed? Like, what determines those special stationary states?
Well, that's where the quantum condition comes in. It's this equation, oint p theta d theta NAHA. Basically, it says that if you take the angular momentum of the electron and you integrate it over one complete orbit, the result has to be a whole number, multiple, of Planck's constant. So n can be 1, 2, 3, and so on.
So again, we're seeing Planck's constant popping up, quantizing things.
Yeah, that's the key. It's saying that the angular momentum can only take on these discrete values. It's not continuous like it would be in classical physics. And this is how Bohr picked out those special stationary states.
Right, okay. So it sounds like this old quantum theory was this weird mix of classical and quantum ideas. Like, they were still using classical mechanics to describe the electron's motion, but then adding these quantum rules on top.
Exactly. It was this very strange hybrid. And to really understand the correspondence principle, it helps to think about a simple example. Okay, let's imagine an electron just moving back and forth in one dimension. Kind of like a pendulum.
A one-dimensional atom.
Right, exactly. So classically, this motion, we can call it omega, it has a certain frequency, omega, and you can break it down into a sum of sine waves, each with a frequency that's a multiple of omega, like omega and so on. We call those harmonics.
And classical physics says that a charged particle moving like that would radiate at all those frequencies, right?
Exactly. It would be emitting light at all those harmonic frequencies. But remember, Bohr said that radiation only happens during these quantum jumps. And the frequency of the emitted light, that's given by the Bohr-Einstein condition.
So we have this clash between these two very different pictures.
Right. And what Bohr noticed was that if you look at transitions between stationary states, where the difference in the quantum numbers, like n, is large, then the frequency of the light emitted during the quantum jump, it starts to get closer to one of the classical harmonic frequencies.
Okay, so that's where the idea of correspondence comes from, this connection between the quantum world and the classical world. And it gets stronger when you look at high energy levels, large quantum numbers.
Exactly. So the difference between those quantum numbers, we can call that tau. In classical physics, that tau would label the harmonic. Like tau 1 is the fundamental frequency, tau 2 is the second harmonic, and so on. And in the quantum picture, tells you how many energy levels the electron jumps down. So the correspondence principle is exploring the connection between those classical harmonics with frequencies and the frequencies of light emitted during quantum jumps.
Okay, so we have some background now. Now let's really dig into this correspondence principle. You said earlier that there isn't one single definition everyone agrees on, which for a philosopher, that's kind of like a flashing sign saying, look here.
It is, totally. And it means we have to be extra careful. Like, we need to separate what Bohr himself was saying at different times from how other people have interpreted it later. And even in Bohr's own writings, it's kind of messy. He talks about all these different connections between the classical and the quantum, and any of them could be part of what he meant by the correspondence principle.
Okay, so you said there are three main contenders for what the correspondence principle is really about. The first one is the frequency interpretation, right? What's that all about?
Yeah, so this one's saying that there's a statistical asymptotic agreement between the frequency of the light emitted during a quantum jump and the frequency of one of the classical harmonics.
Okay, so a few things to unpack there. First, what do you mean by statistical?
Good point. So classically, you'd have this electron constantly emitting radiation at all its harmonics at the same time. But in the quantum picture, you have an atom emitting one photon with one frequency during a single jump. So it's not an exact match at every moment. But if you have a whole bunch of atoms, a whole ensemble, and they're all doing these quantum jumps, the overall pattern of frequencies, that should start to look like the classical prediction. in a statistical way.
And what about asymptotic?
Right, so that means this agreement only really kicks in when you're looking at really high energy levels. Like when the quantum numbers are really large, it's not something you'd necessarily see for those low energy states.
Okay, so that's the frequency interpretation. What about the second one, the intensity interpretation?
So the intensity one, that's also about the limit of large quantum numbers. But this time it's saying there should be an agreement between the probability of a quantum jump happening and the intensity of the corresponding classical harmonic.
Okay, so if a particular harmonic is really strong in the classical picture, meaning it would emit a lot of radiation at that frequency, then the corresponding quantum jump should also be more likely to happen.
Exactly. And because the probability of a jump is related to the intensity of the spectral line you observe, that means the bright lines in the quantum spectrum should match up with the strong harmonics in the classical spectrum.
Okay, that makes sense. And then the third interpretation, the selection rule interpretation, you said that one is kind of different.
Yeah, this one is more about a direct connection, not just an agreement in some limit. It says that each quantum jump that's actually allowed, it corresponds to one of the harmonics that exists in the classical motion.
So if a certain harmonic is missing in the classical picture, then that quantum jump just can't happen at all.
Right. It's like a rule, a selection rule, that determines which transitions are possible. And importantly, this one is often thought to apply for all quantum numbers, not just the large ones.
Okay, so we have these three interpretations, and it sounds like even experts on Bohr don't fully agree on which one is the right one.
That's right. Bohr never explicitly said, this is it, this is the correspondence principle. He talked about all of these different aspects, and that's led to a lot of discussion among historians and philosophers of science.
Okay, well, to try and get a better handle on what Bohr himself was thinking, I guess we should look at what he actually wrote, right? Like his papers from that period, 1918 to 1928.
That's a great idea. It's like detective work, trying to piece together the clues. So the thing is, even though we can trace the idea back to his 1913 papers, he didn't actually start using the phrase correspondence principle until around 1920.
Okay, so what was he calling it before that?
He used the word analogy a lot, but he later rejected that word, saying it wasn't strong enough. He started calling it a law of quantum theory.
So not just a helpful tool, but something more fundamental?
Exactly. He was saying it was a core part of quantum theory, a universal principle that applied everywhere. It wasn't just some trick to make the quantum world look a bit like the classical world in certain cases. And this is really important philosophically. Like, it's about what kind of relationship there is between these two different descriptions of the world.
Right, right. Okay, so in his 1920 paper, where he first used the phrase correspondence principle, what exactly did he say?
Well, he talked about this far-reaching correspondence between the possible quantum jumps and the harmonics of the classical motion. He even said that quantum theory should be seen as a rational generalization of classical theory. So not a complete break, but a continuation in some sense.
That's a really interesting way to put it.
Yeah. And in that same paper, he's talking about both the frequency and intensity correspondences. And he's connecting them to a general rule for transitions, even when the quantum numbers are small. He was saying that whether or not a transition can happen, that's determined by whether the corresponding harmonic exists in the classical motion.
So again, a link between the possibility of a quantum event and something in the classical description.
Exactly. And he also said that the correspondence principle explains why we only see certain spectral lines, like why some combinations of lines just don't show up in experiments. Elisa Berkulich, the philosopher, she's argued that this is where the selection rule interpretation really fits best.
Because the selection rule tells you which transitions are allowed and which ones are forbidden.
Right. And it does that based on the classical harmonics. So in a way, the classical picture is still controlling what can happen in the quantum world.
Okay, so even early on, Bohr was pointing to something deeper than just asymptotic agreement at large quantum numbers.
Yeah, he was. And he keeps going with this idea, like in his 1922 lectures, he uses the example of the Balmer series in hydrogen, which is some of the spectral lines we observe. He talks about these lines as having a correspondence with the first and second harmonics of the classical motion, even though the quantum numbers involved are actually pretty small.
So that really goes against the idea that the correspondence principle is only about the classical limit.
It does. He's focused on the qualitative connection, like a certain type of transition corresponding to a certain type of harmonic. And he keeps saying that whether a transition can happen at all, that depends on whether that harmonic is there in the classical picture.
And then a few years later, you have Heisenberg's matrix mechanics, How did Bohr see that fitting in with the correspondence principle?
He saw matrix mechanics as this like really precise mathematical way of expressing the ideas that were already in the correspondence principle.
Like turning the qualitative into quantitative.
Yeah, sort of. He said that matrix mechanics was working with quantities that symbolize the possibilities of transitions between stationary states in conformity with the correspondence principle. So he was seeing this new quantum mechanics as still being guided by those connections to the classical harmonic structure.
That's fascinating. So even though the math was getting more abstract, the underlying ideas were still the same.
Yeah, for Bohr, the correspondence principle was still this guiding principle, even after modern quantum mechanics came along. Like in his big lecture in 1928, he's still talking about it as this crucial bridge between the quantum and the classical.
Okay, so for Bohr, it was really a foundational idea that stayed with him throughout his career.
Absolutely. And it influenced his whole interpretation of quantum mechanics.
Okay, so I'm curious about how other physicists reacted to Bohr's correspondence principle when he first started talking about it. I mean, it sounds like a pretty radical idea.
It was. And not everyone was on board, that's for sure. I mean, some people just didn't get it at all. And even those who did, they often had problems with it.
Like who?
Well, there were some big names like Sommerfeld, Pauli, and even Heisenberg, who were all skeptical in their own ways.
Let's start with Sommerfeld. He was a big deal in physics back then, right?
Oh, yeah, he was really influential.
Mm.
And he definitely had issues with the correspondence principle. He thought it was too vague, too hand-wavy. He wanted something more mathematically rigorous.
So like more equations, less intuition.
Yeah, he was all about formal elegance. He thought the correspondence principle was kind of mixing up classical and quantum ideas in a way that just wasn't clean. He even called it a magic wand, like Bohr was just waving it around to get the answers he wanted.
So like a useful trick, but not something fundamental.
Exactly. He was also suspicious of the whole idea of analogy. He thought quantum theory needed to stand on its own, not rely on comparisons to classical physics.
Okay, so what about Pauli? He was known for being a bit of a tough critic.
Oh, yeah. Pauli was brutally honest. He thought Bohr was too focused on models, like picturing electrons orbiting the nucleus. He wanted a more abstract mathematical approach. He was also really uncomfortable with the use of orbits in the correspondence principle.
Because orbits are a classical idea, right?
Exactly. He was like, we need to move beyond that. Quantum mechanics is something new, something different.
Right. So he wanted a clean break from classical physics.
Yeah, and he didn't think the correspondence principle was helpful for achieving that. He thought it was actually holding quantum mechanics back. And ironically, his own work, his exclusion principle, that actually provided a purely quantum explanation for something that Bohr had tried to explain with the correspondence principle.
So in a way, Pauli succeeded where Bohr, using the correspondence principle, had kind of failed.
Yeah, you could say that. And then there's Heisenberg, which is kind of funny because his own work on matrix mechanics, it was actually guided by the correspondence principle. But later on, he kind of distanced himself from it.
Really? How come?
Well, it's a bit complicated. But basically, he started to see quantum mechanics as this complete, self-contained theory. And he didn't think it needed the correspondence principle anymore. He called the agreement between quantum and classical a purely formal result. Like it was just a mathematical coincidence.
So like the math worked out, but there wasn't any deep reason for it.
Yeah. And he really emphasized this idea of positivism, like focusing on what you can actually observe and measure and not worrying so much about what's really going on.
That's a big philosophical shift.
It is. And it shows how these big thinkers in physics were all struggling with the meaning of quantum mechanics.
Okay, so I'm seeing a pattern here. A lot of debate, a lot of different opinions, and I guess that's continued in the history and philosophy of science, right?
Oh, absolutely. I mean, historians and philosophers are still arguing about what the correspondence principle really means, how widely it applies, whether it's a law or not, and how it relates to modern quantum mechanics.
So like a full-blown academic debate.
Yeah, totally. Like Max Jammer, who wrote this big book on the history of quantum mechanics, he focused on the frequency interpretation. And he basically said that Bohr was kind of fudging it, trying to make the principle apply everywhere, even when it didn't really fit.
Not pulling any punches there.
No, he wasn't. And then you have Mera and Rechenberg. They also wrote these massive volumes on quantum theory. They had trouble explaining how the principle could be a law if it didn't really work for small quantum numbers.
So more critiques.
Yeah. But then you have Olivier Dirigal, another historian. He takes a different view. He says the intensity interpretation is the key one. And he thinks Bohr was right to call it a law because it relates to quantum concepts, the probability of a transition and the characteristics of the atom's motion.
So a more sympathetic reading.
Yeah. He also argues that the intensity interpretation is actually built into Heisenberg's matrix mechanics.
Okay, so maybe a bit more continuity between Bohr's ideas and the later developments.
Exactly. And then there's Hans Ratter. He has this idea that the correspondence principle actually went through 3 phases in Bohr's work, starting with numbers, then concepts, and finally formal mathematical connections.
So like a gradual refinement of the idea.
Yeah, that's the idea. And then there are more recent interpretations, like Robert Batterman. He sees it as a connection between radiation and atomic vibrations. And Takashi Tanona, he focuses on the role it played in connecting what we observe, like spectral lines, to the theoretical model of the atom.
And of course, we can't forget Elisa Bakulish, who we mentioned earlier.
Right. She's all about the selection rule interpretation.
Mm-hmm.
She thinks it explains why the principle works even for small quantum numbers, why it's a real law, and how it connects to matrix mechanics.
So it's amazing how many different ways people have interpreted this one principle.
And it really is, and it shows just how deep and subtle Bohr's ideas were.
Okay, so all this debate, it makes me wonder how physicists actually use the correspondence principle today, like in current research.
That's a great question. And it's a bit ironic because the way it's used now is often quite different from what Bohr himself was saying.
How so?
Well, starting in the 1930s, people like Max Born, they started to redefine the correspondence principle as this requirement that quantum mechanics has to reproduce the results of classical physics in certain limits.
So like when you have really big objects or really high energies?
Exactly. They were saying, look, we know classical physics works in those cases, so quantum mechanics better give us the same answers.
So it became a test for quantum mechanics.
Yeah, kind of consistency check. Like, if quantum mechanics is the more fundamental theory, it shouldn't contradict classical physics where we know classical physics works.
Makes sense.
And people like David Bohm, they also thought along those lines. Like, they said that quantum laws should average out to classical equations when you're dealing with lots of particles.
Okay, so the focus shifted to this idea of the classical limit.
Yeah. And there are different ways to think about that limit. Like some people, like Richard Leibov, they focused on the frequency spectrum. Like they said the quantum spectrum should approach the classical spectrum when the quantum numbers get really large. But there are systems where that doesn't quite work.
So some wrinkles in that idea.
There are. And then other people, like Hassoun and Kobe, they said you have to consider both Planck's constant going to 0 and the quantum number going to infinity.
So a more nuanced view of the limit.
Yeah. And they even argue that Bohr himself was already thinking about this kind of limit, even though he never explicitly said so.
Okay, so it sounds like the correspondence principle is still relevant today, but in a somewhat different way than Bohr originally intended.
That's right. And it's important to remember that Bohr himself didn't actually agree with this whole classical limit interpretation.
Really?
Yeah, he thought the correspondence principle was much more than that. He saw it as this fundamental principle that was built into quantum mechanics from the very beginning. It wasn't about recovering classical physics. It was about understanding the quantum world itself.
Right, right. Okay, one last thing. We've been talking about Bohr's correspondence principle, but there's also this thing called the generalized correspondence principle. What's the connection there?
Yeah, so the generalized one, it's a much broader idea. It comes from philosophy of science. Heinz Post, he was the one who really articulated it. And he said that any new scientific theory should be able to explain why the older theory worked where it did. Like it should reduce to the older theory under the right conditions.
So like a kind of inheritance principle?
Yeah, exactly. But the funny thing is, Post himself said that quantum mechanics doesn't actually follow this principle very well.
Really? Why not?
It's a bit complicated, but basically he thought there were some fundamental differences between classical and quantum that just couldn't be bridged by this kind of limiting procedure.
Okay, so maybe quantum mechanics is more of a break than a continuation after all.
It might be. But then you have Hans Ratter, another philosopher. He actually thinks quantum mechanics does follow the generalized principle.
Mm-hmm.
And he sees Bohr's correspondence principle as a specific example of it.
Okay, so different opinions again.
Always.
Hmm.
But the main point here is that Bohr's principle is much more specific. It's tied to the historical development of quantum mechanics. Whereas the generalized principle is this abstract philosophical idea about how scientific theories change in general.
Right. Okay, so big picture, I think we've learned a lot today. Bohr's correspondence principle, it's not just some historical curiosity, it's this really deep and complex idea that was central to Bohr's thinking, and it's still being debated and reinterpreted today.
Absolutely. And it's not just about physics, it's about philosophy too. Like how we understand scientific progress, the relationship between different theories, what it means for a theory to be fundamental.
Yeah, that's what makes it so interesting.
And for you, our listener, thinking about all this, it really raises the question, what does it mean for a scientific principle to have so many different interpretations? Does it make it less important? Or does it show us something about how science really works?
Yeah, that's a great question to leave people with. Like, which interpretation resonates with you and why? And what does it tell us about how revolutionary ideas take shape and how they relate to what came before?
Lots to ponder.
Thanks for joining us today. We'll see you next time.